The most powerful feature of Golang is its simplicity of its language. It is so straightforward and so easy to understand. The other beautiful thing about Golang is the ease of use of its concurrency features. Obviously, I cannot cover everything that Golang offers. However, this video should give you a good start when learning its concurrency features. So, why is it even concurrency and not parallelism? Don't worry, I'm not going to go into depth here what actual difference between these two concepts are. But there are a lot of videos out there that are pretty helpful and pretty well explained as well. But generally, concurrency refers to kind of a structured program that can handle multiple tasks. Now, it's really important to know that this can give you the illusion that things actually happen simultaneously, but this really isn't the case. In reality, concurrent tasks may not be running at the exact same time. One example would be multitasking on a single core machine with the help of context switching. On the other hand, parallelism is really about the simultaneous execution of different tasks. Now, this really means that tasks can literally run at the exact same time. And this can happen, for instance, on a multi-core processor. Now, obviously, there are also a few other things and other differences between these two concepts, but I think this really short explanation should be good for now. Now, one more thing before we jump into the code and into the good stuff here. This video will not contain a real-world example. I will probably make a separate video just about the concurrency features of a real-world example. Alright, so let's get finally to the code. So for this example, we are going to kind of start with a order processing system, right? So some orders come in and we want to kind of process them simultaneously or concurrently. So with that in mind, we can kind of start with creating a order struct. And this order struct contains an ID and also a status, which is for now of type string. Now, obviously, you can make this more beautiful by, for instance, defining 3 constants, right? And then giving this status a fixed value instead of a raw string. But for now, I will keep it simple so that we do not get really confused. Alright, now to create the orders, we are going to create a utility function called generateOrders. And in the end, this function just returns a slice of orders. And here it is important to know that this is a pointer of order. Right, we're going to explain why in a minute. And this function can take in a count, which is an integer. So we want to generate n amount of orders. Right, so now we are going to create a simple slice by just saying make, right? Or in this case, it is a fixed array. And we're going to say order, right? And then the amount is count. So this basically initializes an array or a slice with the count of count, right? So in the end, we now have a order slice with empty elements of the amount of count. All right, and in the end, we just return orders for now. And what we're going to do now is basically just iterate over the count. And now we want to kind of fill in our order slice here. So what we're going to say is orders at the position I, and then we're going to create a new order. Now this order has the ID of I plus 1, so it starts at 1 and then goes to count, basically inclusively in this case. And for the status, for now, we just say pending, right? Because we haven't processed the order. Now, you may wonder, why do we actually have to use a pointer here? Because in the end, we want to manipulate or modify the orders, right? With the status, for instance. And this also makes the slice creation and this whole function more efficient. All right, and now let's just create some orders, right? So we say orders and then we make use of the generateOrders function. And in here, we say 20. So in the end, we now have 20 orders. Now finally, what we want is a simple printline statement, right, that all operations completed, and that's basically it. Now what we want to do is create another function called processOrders, right? So what we're going to do is maybe skip this because it's not important. We're going to say processOrders. Now this processOrders takes in a order slice, and in the end we can manipulate the orders here. That's why the pointer is there. And then we are going to iterate over our pointers. And in the end, we are just printing something, right? And then we want to kind of simulate some work that is going to be needed in this function, right? So for instance, you can imagine sending an HTTP request or some sort of request to another microservice, for instance, where it actually processes the orders or something completely different, right? In this case, we are just going to simulate the work here. And to kind of stretch this work, we're just going to say time.sleep. So we are sleeping here for a while. In this case, the function or the for loop in this case sleeps for a few seconds. And we make use of time.duration, right? And then we're going to generate a random integer between 0 and 500. And we now multiply this with millisecond. All right, with that in mind, we can now process the orders here. So let's say process orders, and then we say orders. And if you now run this, obviously we process the orders, right? This should work, right? So what we're going to say is we're going to create 2 additional functions to really complete this use case, and then we can finally apply the Goroutines here, or the concurrency features. And what we're going to create is basically a new function called update order statuses. And in the end, we take in a order slice again. In here again, we are looping over our orders again. And in here again, we are just going to sleep for some milliseconds, right? Then we're going to randomly select a status of processing, shipped, or delivered. And in the end, we're going to update the order status, right? And then we are just printing something here. So what this function basically does is just update the statuses randomly, right? Sequentially, in sequential order. And again, I'm just going to create a basic utility function to print our orders here. And this now is pretty basic to understand as well, pretty simple. It's called report order status. In the end, it is going to loop over 5 times, right? So it's going to print 5 times the order status. Then we're going to sleep for 1 second, right? Each iteration. And then we're going to print the status of all our orders, right? There's no real fancy logic here, so I'm going to skip further explanation. All right, then let's go back to our main function finally. And now we want to update the order statuses. Right? We're passing in the orders, and then we are going to report the order status with the orders here. Again, this is just a really simplified example. We are now going to apply finally the concurrency features. All right, and the first thing we are going to cover are Goroutines. So what is actually a Goroutine? Now a Goroutine generally is somehow a lightweight concurrent function that can run independently alongside other Goroutines. And this Goroutine is not even managed by the operating system. It is more managed by the Go runtime. It's really important to know that these Goroutines are extremely cheap to create, with only just a few kilobytes of stack space. Now these obviously make them more efficient than traditional threads. Now it's really important to know that this runtime includes a scheduler that kind of manages the Goroutine and distributes the Goroutine across the CPU cores. And in the end, you can really create thousands of Goroutines, which can make your program more efficient, but this cannot always be the case. So really be sure when and why you actually apply Goroutines. Obviously, you have to avoid spawning massive or really excessive Goroutines, right? Because this can lead to resource exhaustion, for instance. All right, and what we're going to do now, we are just going to run quickly the file here. And what we get is the sequential functionality of our program, right? It basically processes the orders, then it updates the statuses, and then it prints the statuses 5 times. And now we're going to make this concurrent. What this basically means is we are going to apply 3 Goroutines here. And you can apply a Goroutine with just 2 letters, which is basically G and O, right? And with this, we now created a Goroutine, right? This is our kind of first created Goroutine, which is pretty cool. Now it's really important to know that this Goroutine here, we actually spawn with this Go keyword, now runs concurrently with the main function. Now what this means is we can obviously apply this to our update order statuses as well, and we can apply this to our report order statuses as well, right? And now we have 3 Goroutines. Now what is really important to know, if we now run this code here, we don't see anything, right? No orders are processed, no status is updated whatsoever. And the whole reason for that is because we spawn these 3 Goroutines in the background, right? And the main function obviously proceeds with its execution. What this basically means is we create the orders, right? So we generate 20 orders. Then we spawn the Goroutine and we execute the process orders function We do the same thing with the next two Goroutines, and then we just print, and that's basically it, right? Then obviously the main function exits, and therefore all the Goroutines in the main function are also terminated. Now there are basically three solutions to this problem. The first one would be time.sleep, right? The problem with this is because all of the randomness, we don't really know when this program actually ends, right? So this solution is not really applicable for us here. The second solution would be to use scanline. The problem with that function is that it requires user input, right? And obviously we do not want to always like press the enter key or press the spacebar, for instance, to terminate this program, right? We want to terminate this program whenever the Goroutines finished. And for that, we can actually make use of a WaitGroup. Now you might wonder, what is a WaitGroup? First of all, WaitGroup is part of the concurrency features of the Golang language. And it's basically a synchronization primitive in Golang that is used to basically coordinate multiple Goroutines. Now again, a WaitGroup basically allows you to kind of wait for a collection of Goroutines to kind of finish executing before executing the next step. And you can really imagine this WaitGroup as a counter, right? Which really increments whenever the Goroutine starts, or whenever you say that the Goroutine starts, right? Or whenever you add something to the counter, and whenever you say kind of done, right? It decreases and it decrements the counter, right? So let's make this program here more beautiful with WaitGroups. So what we're going to do is create a simple WaitGroup, and that's it, right? We've now created our first WaitGroup here. Now, it's important to note that this kind of initialization is the same as this case here, right? Where we say WaitGroup and we kind of initialize WG with sync.WaitGroup with an empty struct of type WaitGroup. Right? It's basically the same thing. Obviously there are some differences, but it's kind of in the end the same. Right? And now what we can do is we can always add something to our counter whenever we start a Goroutine. Right? And in the end, we have here 3 Goroutines. So what we want to do is we want to wait kind of 3 times, right? I want to increment the counter, the WaitGroup, by 3. And in the end, the WaitGroup will really wait and will kind of stop the execution whenever the counter, or the WaitGroup in this case, becomes 0 again. So what we can do is we can just say wg.add 3. Right? And now with this add function, we increment the WaitGroup or the counter by 3. Now, how can we now wait until these 3 Goroutines actually finish? What we can do is just call the wait function. That's basically it. And this wg.wait, or this wait function in general, really just blocks the whole execution until the counter and the WaitGroup becomes 0 again. Right? This is really important to know here. Obviously, because we spawn 3 Goroutines, these run in the background, right? But the main function will wait until the counter or the WaitGroup becomes 0 again. Okay, and now how can we actually decrement the counter, right? Because we obviously need to decrement the counter to become 0 again, because right now it is just stuck at 3 the whole time. Now there are kind of 2 solutions for that. The first one would be to make use of the WaitGroup in the main function, which we are going to do here in a minute. And the second solution would be to just pass in the WaitGroup to our process orders function and to all the other functions, and then use the functionality I'm going to demonstrate in a minute in this specific function. What we can do is, this is not the only way we can spawn Goroutines. Right? So what we could do is to create an anonymous function as well. And this anonymous function will be directly executed, right? So what we can say is func, and then with these 2 round brackets or parentheses, this function, this anonymous function, is getting executed immediately. And what we can do is we can spawn this function as a Goroutine as well. So we can say go func, and then this whole block and this function will be executed in a Goroutine. And what we can do now here is call process orders. However, what we can do is we can say wg.done in this Goroutine, right? So we are not passing the WaitGroup into the function directly. We are just going to create a Goroutine And then whenever the process orders function is done, so these two operations are executed sequentially, right? So the process orders function is first executed, and then this line is executed as well. All right, so we can remove this. What is really best practice with the WaitGroup as well would be to make use of defer in this case. All right, and now we have basically the decrement functionality of our WaitGroup in our Goroutine. Now we're going to do the same thing with the other functions as well. So we're going to say defer wg.done, and then the same thing here. Now if we run this program, we now have basically all the functions are now run concurrently, which is pretty cool, right? So we see, for instance, that the 20th order is actually processed in the end, right? And in between we have like a few print statements, and we actually start with updating the order like 2 times, right? And then processing the order and so on and so forth. All right, so in the end, a WaitGroup is pretty cool to synchronize different Goroutines. But a few things can still go wrong with these specific Goroutines here, whenever multiple Goroutines access the same data. And this is where we are going to introduce a mutex. Now, a mutex generally stands for mutual exclusion. And in the end, a mutex is a locking mechanism that ensures that only one Goroutine can access a specific section of your code. And mutexes are basically used to prevent race conditions, right? Because these are really common among Goroutines and generally threads as well. And you can imagine these mutexes as somehow a traffic light, right? Which in the end allows only one car, or one specific Goroutine in this case, to pass through an intersection or a block of code at a time. And what actually happens when a Goroutine tries to attempt and access a mutex, or tries to attempt some data between the locking mechanism of the mutex? Basically, these Goroutines are queued in a first come, first serve order. And then whenever the locking mechanism is unlocked again, right, so the mutex is kind of available again, not locked anymore, then the queue is actually processed, right, and the Goroutines continue its execution. Alright, now how can we actually add a mutex? For that, we are going to add a mutex to a specific order, right? So every single order will now include a mutex. And we are going to say mu and then sync.mutex. And now we have our first mutex here. Oh, and by the way, I quickly changed the functionality of the report order statuses, right? To basically just print once and not print in a separate Goroutine as well, because it doesn't make a lot of sense to spawn this function in a Goroutine. And also I've decremented, because we now only have 2 Goroutines, the WaitGroup to 2. Hopefully that makes sense why we actually did this. And what we are going to do now is we are going to kind of refactor the functionality a little bit. What we're going to say is, instead of updating all the orders, we are just going to update one order. So I'm going to quickly refactor this function here. And now we kind of only update one order at a time. And what we're going to do now is we are going to modify this Goroutine here. And what I want is, maybe I do want to have 3 kind of workers, right? They are called workers. And I'm going to make a separate video about worker pools and all that funny stuff. But we are going to keep it simple here and just create 3 Goroutines that are going to process one order at a time, right? And in here, we are going to loop over the orders again. And then we are going to say update order statuses, or let's call it update order status, right? And we are passing in the order. Now let's quickly comment out the process order functionality, and then we are going to increment the WaitGroup here by 3, because now we have 3 Goroutines again. And what we're going to do now is we are running the program. And now everything works as expected. I mean, kind of, right? Because now we are going to apply a mutex here. And to make things more clear why we actually need a mutex, let's just quickly create some global variables here. Let's just create total updates integer, right? And then we are going to kind of create a global mutex as well, which we are going to call update mutex. And for now, let's just print here the total updates. Right, now back in our update order status function, we are now going to update the total updates, right? But in a really weird manner. So what I'm going to show you is we are going to say current updates is equal to total updates, right? Because maybe then we want to do something with the current updates, right? We want to process them or send them to some other service again, right? And we are going to simulate this by just waiting 5 milliseconds again. In the end, we do have the current updates here for whatever reason, right? And then we say total updates is equal to current updates plus 1. Now, an experienced programmer might notice that this program here and this specific block will be error prone. Specifically when you have a few Goroutines. Because right now we have 3 Goroutines. Now, if we run this code here, what we would expect would be 60 updates. But we do not get 60 updates, we only get 54, right? And then we only get 57. And it's not the expected total updates, right? What we can do to prevent this issue is to lock this kind of functionality whenever we update the total updates, right? And you would do the same with the order mutex whenever you have this functionality here, right? So you would say order.mu.log, right? This will now lock the mutex and it will lock all the Goroutines out of this functionality and it will queue up the Goroutines. And then whenever the mutex again is unlocked, which is here, then in a first come first serve order, it processes the Goroutines again. Right, so it unlocks the log, and then again, whenever another Goroutine wants to update the order status, we're going to lock the mutex again, and then all the other Goroutines or the following Goroutines have to wait. And we have to do the same thing for our current updates. And this will be actually visible, that's why I actually implemented this current updates functionality. And what we can do is we say update mutex.log, right? And then what actually is good practice here is to use defer again and then update mutex.unlock, right? Because in the end, we want to unlock the mutex again because we've locked it. Now, whenever we run this code, we see a much better processing stage of kind of updating the statuses. And we do receive the value 60 for our total values, right? We can run the program again. We will always get 60. So this is pretty cool. Now, why is this the case? It's pretty easy to understand, right? Like I said in the beginning, the first Goroutine approaches this log statement and just locks the update mutex, right? Now it kind of processes this kind of code, and then maybe another Goroutine approaches this log statement, and now it waits until this log functionality is available again, right? Now let's get back to our first Goroutine. It processes this code, and then it unlocks the mutex, right? Now it says the mutex, okay, I'm done with my processing logic, right? And then the second Goroutine can go ahead and lock the mutex again, because now it's available, it's unlocked again, and then it can start its work here. So hopefully this was easy to understand. Now let's get back to another really cool feature of the concurrency features of the Golang language. And now I'm actually talking about channels. Now channels, you can think of channels of some kind of communication conduits, right? Between Goroutines that allow to send and receive values. This could be also structs, but can also be simple numbers like integers. And these channels serve as a typed thread-safe way for Goroutines to kind of synchronize and exchange data. I'm going to show you what I mean here in a minute. Now these channels help to avoid really common threading issues like I said before, race conditions or even deadlocks. And you can imagine a channel like a pipe. Right now this pipe has a specific data type, which could be an integer, to only carry this sort of data through the pipe. And then the data flows through the pipe from one direction to another, from the sender to the receiver. Now it's important that multiple senders and receivers can use the channel, but it's really important to know that Go ensures that only one operation happens at a time. Alright, so let's get into the first channel type, which is the unbuffered channel. Alright, now what I'm going to do is going to clean up the code a little bit. I'm going to remove the update order status here, and in the end remove this function, right? And then we don't need the total updates or update mutex, right? And then we can uncomment this and remove this print line. And now what I want in the wait group is 2. So we want to spawn 2 Goroutines, and we're going to create a Goroutine with the generate orders function here. And what we're going to say is go func again, right? And then this anonymous function is going to be executed again. Now in this function, we're going to say defer wg.done to decrement the counter. And then we are going to loop over our generated orders here. And then we are going to print line something that just say done with generating orders, right? Because now what we want is we want to generate orders in a Goroutine, and we want to receive these orders in another Goroutine, right? And that's where a channel comes into place. Whenever we want to send data from one Goroutine and receive it in another Goroutine. Now how we're going to create a channel is pretty simple. Let's just say order shen, and then we can, or we need to use the make function here, which in the end just creates a channel for us whenever we define the type shen in this case, right? And this channel types requires another type, which in the end is the data type that we want to send or receive for this channel. Now again, this value or this data type can be a struct, but it can also be a simple integer. In this case, we are going to make use of pointer order because we want to manipulate the order maybe. And this is really also the only way we can create these channels. Now what we can do in our loop here, let's just rename orders to order because we process one order at a time sequentially. We can just say order shen, right? Because now we actually generated the order, right? And now we want to send the order through the channel. And what we're going to say is order shen. We're going to make use of this arrow here, which signals Golang that we want to send data into the channel, right? This arrow points into the channel, and that's why we want to send the data into the channel. And we are going to send the order into the channel. Now, what is really important is that this is a blocking operation until there is an available receiver, right? And what we can do now is we can kind of change this process orders functionality to really accept this order channel and receive the order. Now what we're going to say is we're going to refactor this code as well. We're going to again spawn a Goroutine here, and then we're going to pass in the wait group. Now you will actually see here in a minute why we do this. Also, we can get rid of report order statuses quickly. And now back into our main function. We now do not accept the orders directly. We only want a order channel, right? Because we want to receive the orders from this channel. Then we go to our process orders function. And in here we are going to, let's just first declare the wait group here, right? So this is now a pointer to a wait group because in the end, we need to say wg.done. We need to decrement the wait group, right? Because now this function is done. And now we define the order channel here. So we say order chan. And what we can do now, we can say chan and then order, right? This actually would work. Now the problem with that kind of syntax is that it's not really specific because we can make this kind of channel type more specific. In this case, like I said before, in the process orders function, we only want to receive the orders, right? We do not want to send anything in the channel. Now with this specific parameter syntax here, we specify that the channel can send and receive values in our process orders function, right? But we don't want this. We only want to receive values. And that's why I've actually specified the arrow here, right? So the data is coming out of the channel. And that's why the arrow is pointing out of the channel. Now, if we want to specify that the channel is only sending values, we just say that it should be a send only channel, right? And in this case, like I said, it should be a receive only channel. And this is a bit more strict because then in this function, we really cannot send any values through this channel. Now what we can do is we can say order and then we range over the order channel. Now this is pretty strange, but all it means is that it kind of waits until it receives a order from the order channel, right? And it loops over the order channel until the order channel is closed. So this is not your typical range loop, right? Like you would range over your slice or array, for instance. This really waits until the channel is closed and really always tries to receive the values whenever a value comes in to the channel. And now order is of type pointer order, right? And what we can do now is basically execute our logic here. Okay, that is pretty cool. Is that all? Let's quickly find out. Let's run this program. And what we see is obviously the sequential processing of our orders. And then we get an error, which in the end is a deadlock. Now a deadlock really means that we somehow have a receiver that is still trying to receive values, but there is no sender in place, right? But it can be also vice versa. So whenever we have senders, but there is no receiver, and it tries to send data forever, likewise for the receiving, right? It tries to receive forever. So for instance, in this case here, this range loop would loop forever, right? Because we try to receive values forever, but there is no sending functionality anymore. Because whenever we end this loop, which is 20 in this case, right? By 20 orders, the channel is done and we do not send any data anymore. And that's why this deadlock occurs. Now what we can do to kind of tell the receivers that this channel is closed, we can close the channel, right? And that's how the receivers know, okay, we need to end, right? And we need to end the receiving mechanism in this case. Now here it is really best practice to always close the channel from the sender side. So for instance, if you have a function that sends data to a channel, this function should really close the channel, right? In this case, we do this in this Goroutine here by just saying close, and then we say order chen. Now this says really that no more values come into the channel, right? And the receivers should really calm down and terminate it kind of receiving logic. And this can be also used in a defer statement here. Okay, let's just quickly run the program again. And now we do not get any deadlock anymore, which is pretty cool. All right, now with that in mind, we have also so-called buffered channels, right? Right now, we only use unbuffered channels. And these unbuffered channels are synchronous, right? So the sender blocks until the receiver is ready to receive the data. And you would actually use these unbuffered channels whenever immediate processing and synchronization between Goroutines is crucial. And this really ensures that the data exchange between these Goroutines and between this channel really happens simultaneously between the sender and receiver. Now these unbuffered channels really provide a guarantee that this data is received as soon as it is sent. And it's really useful for ensuring tight synchronization between channels, right? Now coming to buffered channels, this is not a buffer channel like I said before, they are created with capacity and are really good for scenarios where asynchronous communication is needed. And here it's really important to know that the sender only blocks when the channel is full. Now this really means that these buffered channels can hold multiple values before a receiver is ready. And we can actually specify this capacity. This is really useful for managing, for instance, bursts of data or decoupling sender and receiver timings. Now there's definitely so much more to talk about channels, but I'll probably make a separate video about them because they are so important to understand. All right, let's just quickly demonstrate here a buffer channel. Now what we can do in the make function, we can also specify the capacity of our channel. And what we can say, because we have 20 orders, right? We know that these will be kind of 20 orders in our channel. We can say that the capacity is 20. And now we've created a buffer channel which can hold 20 values before a receiver is ready, right? Now let's just quickly run this program here. And what we actually see here in the beginning is that the Goroutine is actually done with generating the orders, right? Before they're actually processed. Now without this buffer channel, right? If we make it unbuffered again, we've actually seen that the Goroutine which generates the orders was done whenever all the orders are kind of processed. Now, why is this actually the case? Again, because we use a buffered channel here, and we fill this channel with 20 values immediately, right? So this channel now actually has 20 values inside of it. And now you might actually wonder why the receiver still processes the orders, but we've already closed the channel, right? This is kind of weird. Why does it do that? Now, the reason is pretty simple. If we try to send data through the channel after we closed the channel, there will be a panic. But we can still receive values that were already sent to the channel before it was closed, like in this case, right? Because we kind of have 20 values in our buffer channel, and the receivers still want to receive this data. And really, this close function then, this closing of the channel, in the end really means that the senders can close the channel to signal no more data, while the receivers can finish processing all the data that was sent before the close. Right? That is really important to know. And that's why this buffer channel works in this case. Now, the final construct I'm going to actually demonstrate here and explain is the select statement. It is so important as well. Now, the select statement is a control structure designed to handle multiple channel operations simultaneously. You can think of this select statement as a special kind of switch statement. But in this case, this switch statement or select statement is specifically designed for channel operations. It's really important to know that this select statement waits until one of the channel operations, I'm going to demonstrate this in a minute here, which can be sending or receiving data, becomes ready to execute. And that really means that it can wait on multiple channel operations simultaneously. And because the select statement is somehow a blocking mechanism as well, like the switch statement, there's also a default statement, and then the select statement is not blocking anymore. Now, whenever we do not have a default case for our select statement, the select statement just waits until one channel operation becomes ready for execution. And whenever multiple channels are ready simultaneously, which can also happen, then the select statement, or Golang in this case, just selects one randomly. Now, there are a lot of use cases for this select statement, but common use cases could be timeout handling or event multiplexing. Right, so let's get into the code here. Let's just create another channel called processed chan, right, which in the end is the same type, right, chan of order, and it is a buffer channel which has the capacity of 20. Now we're going to keep this first Goroutine as it is here, right? Then we're going to hop to the second Goroutine, and we're going to pass in the processed chan in here, right? Now let's go to the process orders. And in the process orders, we're going to rename this order chan to in-chan, because this is an input channel, right? We are only kind of receiving the data, right? Or receiving the orders from this channel. And we're going to say out chan, which is a send only channel, right? So in this function, we're going to receive the data from the in channel, and we're going to send the processed order to the out channel, right? Hopefully this is clear. So in the end, we have a receive only channel and a send only channel. Cool. Now in here, what we can do is just create an anonymous function as well. And we're going to take this down into here. And then we're going to close the out channel to prevent deadlocks, right? Because in the end, we are now the sender functionality or the sender function, and therefore we're going to close the out channel. Now and then we are going to sleep again, just remove the printf for now. Obviously order chan becomes now in chan, and then we are going to update the status to be processed. And then we are going to send the order into the out channel. So now whenever data comes into the input channel, right, or the in channel in this case, whenever an order is generated or comes into the channel, it is being processed. The status is being updated, right? And then this order is going to be sent into the out channel, which we are going to handle in a minute here, right? Hopefully this was clear. All right, let's quickly create a new Goroutine with an anonymous function that will execute immediately, right? We're going to say defer wg.done, right? Because obviously we have to wait for this Goroutine. We're going to increase the WaitGroup here. There's a much more efficient way to do this, but obviously this is just for demonstration purposes here. Now, and then we are going to create an infinite loop. And this can look really scary, but hold on for a minute here. We are going to make use of select, right? And this select is specifically designed for our channel operations. And then we're going to say processed order, and then OK, and then processed chen. Okay, so I'm going to quickly explain why do we have this infinite for loop, what is the select, and what is this case? What does all of this mean? So first, this infinite loop is there to continuously check the channels, right? Because we want to always check the channels if there are any updates or if there's basically any really processed order. And now the select comes in, right? And this allows again for asynchronous communication on multiple channels. Now, because we will not have a default case, this select will wait until one channel operation becomes ready, right? Until one order was processed in this case. Now, instead, if we have a default case, which can be a thing in the select statement, this select becomes non-blocking and executes the default case if no channel is immediately ready. Now, what I've said here in this case is basically we wait, right? We want to receive the data from our processed channel and we save this in the processed order. Now I've added another OK here, which in the end is a Boolean, and this OK really indicates if the channel has been closed or not, right? So if OK is false, then the channel has been closed and we want that this loop, this infinite for loop, should exit whenever the channel is closed. So let's just do this. Let's just say if not OK. So if the channel is closed, we're going to say return, and let's just print something to the console by processing channel closed. Pretty straightforward, pretty easy. And whenever we do have a processed order and the channel is not closed, we are going to print something to the console again. And we are just going to say processed order, right? And then we just print the ID and the status. Okay, that's pretty cool. Let's just add another functionality here, because maybe we want some sort of timeout, right? And that's where another case comes into place. So we say case, and then we say time.after, right? And this after takes an iteration. Let's just say that we want that this timeout is actually executed after 10 seconds. So basically in the end, if no operation really has occurred in 10 seconds, we want to print a timeout and return this infinite running loop. And because this after returns a receiving channel only, this can also be the case that the return type can be a channel, a send only channel or a receive only channel. In this case, it is receive only. Because it is receive only, we can also receive this kind of case statement whenever the timeout occurs, whenever 10 seconds are over. And after that, like I said before, we just return and print something to the console. Right? And this should be basically it. Now, it's really important to note that if no other case is ready within 10 seconds, this case activates, right? This timeout activates, indicating a timeout. All right, so to reiterate this select statement, what we have is a really basic infinite for loop, right? Nothing fancy here. And then we have this select statement specifically designed for channel operations. In here, we have a case statement, right? Which waits until a received value comes from the processed channel, right? Then we do something with that, right? We check if the channel is closed, right? If it is closed, we want to kind of terminate the for loop here. And if no other case is ready after 10 seconds, right, we want to run this case here, and then basically we have a timeout. All right, so let's quickly run this program. And what we get is a pretty basic program, right? We have the processed order, processing channel is closed, which is in the select statement, right? And then we have all operations completed. Now, to kind of demonstrate this time after, this timeout, right? If we say 1 second, obviously this will still not really be the case because the timeout will be reset every time we have the case. Right now, if we change this to be milliseconds instead of seconds, right? Let's just say 300 milliseconds. What we get is that we are done with generating orders, and then we get the timeout waiting for operations, right? And then sometime after we get all operations completed. Now you can optimize obviously this whole program as well if you want to, right? So for instance, now it takes a little bit of time to kind of terminate this process orders functionality, but you can try this on your own. And there we go. This should give you a basic understanding of the most used Golang concurrency features. Now, obviously there's so much more specifically to the concurrency features of the Golang programming language, like worker pools, error propagation, or the context package. And if you are curious about a real-world use case using some of the concurrency features I've discussed in this video, feel free to check out this video here whenever it comes out. Anyway, thank you so much for watching, have a lovely day, and bye bye.